This is the last video of the alcohols topic. We've covered everything here, including aldehydes, ketones, and carboxylic acids, and know what they are and how to draw these. What we're going to do now is look at the oxidation reaction again of alcohols to make aldehydes, ketones, and carboxylic acids, and see how we can set up different apparatus to create a better yield for aldehydes or carboxylic acids in the oxidation of primary alcohols. So just to recap on primary alcohols, when we oxidize primary alcohols using aqueous acidified potassium dichromate, the primary alcohol initially oxidizes to become an aldehyde, and the aldehyde can oxidize as well to form the carboxylic acid of the alcohol. Now you can actually control whether you get more of the aldehyde or more of the carboxylic acid by using different apparatus. If we want to get more of the aldehyde and reduce the amount of carboxylic acid we want, then we want to, as soon as we produce the aldehyde, remove it away from the oxidizing agent to prevent it from further oxidizing. And if we want to produce more of the carboxylic acid, we want to keep the aldehyde within the oxidizing agent and encourage to further oxidize to give the carboxylic acid. So when we want to oxidize a primary alcohol to give more of the aldehyde rather than the carboxylic acid, we will set up a distillation apparatus like this, which we've seen before when we did this experiment on synthesizing haloalkane from the alcohol, and we set up this apparatus, which is the same as on the previous diagram. So we would have the primary alcohol and the oxidizing agent, the aqueous acidified potassium dichromate, in this container, this pear-shaped flask or a round bottom flask, and we heat this, and the oxidizing agent will oxidize the primary alcohol initially to form the aldehyde. Now, an aldehyde has a lower boiling point than the respective alcohol because the alcohol can form hydrogen bonding between its molecules. So alcohols have a higher boiling point than their respective aldehydes, as the alcohols can form hydrogen bonding between their molecules, which are stronger than the permanent dipole forces and the London forces that form between the aldehyde molecules. So if we heat the mixture to the boiling point of the aldehyde, as soon as the aldehyde is produced, it would boil off and vaporize away from the oxidizing agent, leaving the alcohol, which has a high boiling point, to remain as a liquid here. The aldehyde then will be condensed and collected as the major product because it's condensed away from the oxidizing agent and preventing it further oxidizing to give you the carboxylic acid. So during the oxidation, we need to keep an eye on the temperature of the vapour that's coming off into the condenser to check that it is the aldehyde that is being collected. As we heat the mixture, the temperature will rise to the boiling point of the aldehyde, and at that point the vapour that's been collected will be the aldehyde, and the temperature shouldn't rise until all the aldehyde has vaporized away, meaning that all the alcohol has converted to the aldehyde. Any aldehyde that didn't boil off away from the oxidizing mixture will further oxidize to form the carboxylic acid. So as long as we keep the boiling point below the boiling point of the aldehyde, we will still just collect the aldehyde, as the boiling point of the carboxylic acid is higher than the aldehyde, as it can form hydrogen bonding between molecules. Now, the example has been quite strict in marking the diagrams of apparatus, so make sure you practice drawing these diagrams correctly. What they don't like you to do is draw the condenser fused with the rest of the equipment. This is a separate piece of equipment to the connector here, and this is separate to the flask here. A lot of students just draw all this fused into one piece of apparatus, and that'd be marked wrong in an exam. Now, in the other case, if we want to have a high yield of carboxylic acid when we oxidize primary alcohol, we use a different set of apparatus to encourage the further oxidation of the aldehyde to become the carboxylic acid. So what we want to do is to condense any of the vapour of aldehyde that escapes from the oxidizing agent to condense back into the oxidizing agent so it can further oxidize into form the carboxylic acid. And to do that, we heat the mixture under reflux, and I'll show you how to set up the apparatus and draw the diagrams to show heating under reflux. So first of all, we're going to draw the container in which the reaction is going to occur. So we can draw a pear-shaped flask or a round bottom flask. We then clamp the flask, and this is how we draw clamps. We then draw two lines to show in the tube of the condenser within the flask, and then we draw the outer tube of the condenser where the water will flow through. So we draw one side like that, where the water will go in here, and then we draw this side like this, so the water will surround the inner tube. We always fill the condenser from the bottom, so we write cold water in and water out here. We can draw the mixture in the flask, and we can add some anti-bumping granules, and then we label heat. We don't need to draw a Bunsen burner, we just write heat to heat the mixture. We can label the condenser and the clamp. The most common mistake is people put a bung on here. We don't put a bung in the top of the condenser, because as you heat this, the gases will expand and there will be a build-up of pressure. So we don't have a bung here. So usually we choose a suitable length condenser so that any vapour that does escape will be condensed back before it reaches the top of the condenser. We don't put a thermometer like we did for the simple distillation, because we don't need to really monitor the temperature of the vapour coming off here, because all the vapour we want to return back into the mixture. So we can use heating under reflux to get a high yield of the carboxylic acid if we're oxidising a primary alcohol, or even to oxidise a secondary alcohol to give a ketone, to ensure all the secondary alcohol reacts fully and oxidises to form the ketone, rather than have any of the secondary alcohol left over unreacted. So to summarise then, in order to control which product we're going to get high yield of in the oxidation of primary alcohols, whether it's the aldehyde or ketone, we will set up different apparatus for the oxidation of the primary alcohol. So to produce a high yield of the aldehyde, we're going to use a distillation setup where we've got a suitable container like a pear-shaped flask or a round bottom flask, and we're heating the mixture of the primary alcohol with the aqueous acidified potassium dichromate, and any aldehyde produced would immediately condense away from the oxidizing agent to prevent it further oxidizing. And this is because any aldehyde form will boil at a lower boiling point than the original alcohol, because it doesn't form hydrogen bonding like the alcohol molecules can. So the aldehyde can be condensed away from the oxidizing agent to prevent further oxidation to the carboxylic acid, which will also boil at a higher boiling point than the aldehyde produced, and therefore won't escape into the container with the aldehyde. And any carboxylic acid made will remain in the reacting mixture unless we raise the temperature high enough to reach its boiling point. However, if we want to produce a higher yield of the carboxylic acid rather than the aldehyde when we oxidise a primary alcohol, we will heat the reaction mixture under reflux, and this is how we draw the apparatus. The most common mistake people make with this diagram is they put a bung or a thermometer here, which we don't do. So refluxing is the continuous reboiling and condensing of a reaction mixture in a reaction vessel like a round bottom flask or a pear-shaped flask. And refluxing is used to ensure any aldehyde produced in the oxidation of primary alcohol condenses back into the oxidizing agent so it can further oxidize to form the carboxylic acid. We can also use heating under reflux to oxidize secondary alcohols to produce ketones and ensure a high yield of ketones produced, because heating under reflux will ensure any unreacted alcohol that escapes can condense back into the oxidizing mixture and convert to the ketone. So this covers all the topics of alcohols. We looked at how to name alcohols and classify alcohols into primary, secondary, tertiary alcohols. We looked at the physical properties of alcohols and explained them in terms of hydrogen bonding. We then looked at how to make alcohols from alkenes through hydration and also through hydrolysis of haloalkanes. We then looked at reactions of alcohols. We looked at combustion. We looked at how to write balance equations for the combustion of alcohols and the fact that it is a type of oxidation reaction. Then we looked at another type of oxidation reaction, which is not burning the alcohol, and that's using oxidizing agents like acidified potassium dichromate, and we produce an aldehyde, ketone, or carboxylic acid depending on the type of alcohol we use. So primary alcohols produce aldehydes initially, and then these aldehydes can further oxidize to carboxylic acids. Secondary alcohols oxidize to ketones, and tertiary alcohols cannot be oxidized by acidified potassium dichromate. Then we looked at some revision of reactions we've done before. So we looked at dehydration of alcohols to make alkenes, and we saw this when we did alkenes topic. We dehydrate an alcohol by heating it with a concentrated sulfuric acid catalyst. And then we looked at the substitution reaction to form haloalkanes from alcohols. And we do this by using a sodium halide and concentrated sulfuric acid to form the hydrogen halide in situ. And then in this video we looked at how we can control the yield of aldehydes or carboxylic acids in the oxidation of primary alcohols by using different apparatus. So we use a distillation apparatus to get a high yield of aldehydes So we distill off the aldehyde away from the oxidizing agents to prevent it from further oxidizing. And then to get a high yield of carboxylic acid, we would heat under reflux to ensure the alcohol oxidizes to the aldehyde and then further oxidizes to the carboxylic acid to give a high yield of carboxylic acid. We can also use heating under reflux for secondary alcohols to ensure that all the secondary alcohols convert to ketones.